Good morning, ladies and gentlemen. My co-authors are Devansh Patel and Chichanok Plisujai, who finished their master's degree with me a year ago, and this is part of the work that they conducted. The idea, let me give you some background on the subject. Phoenix Metropolitan is about 100 miles by 100 miles, and about 10 years ago, there was a move to develop light rail system for transportation. So one line was created, which goes from northwest to southeast of the city of Phoenix. And in this process, it became quite popular, and somewhere about 60 to 70 million people started using it. And then there was a whole issue of can be extended to the other lines. And that idea necessitated to consideration of 2 or 3, some kind of a transportation, a regional plan. There was a 0.7% tax that was implemented. And based on that, some of the dots that you see, in 2023, the 2 projects were selected as the next extension. However, the idea here is basically 5 miles in one direction and 1 mile in the other direction, 2 miles in the other direction for this growth. However, there was a lot of pushback, especially by some of the business owners along the line, simply because of the time and delay that it would take, as well as the cost. So the cost was astronomical. We're talking half a $500 million for these projects. And then at the same time, it would take about 9 months or so per mile to just simply construct it. So it would take 2 or 3 years. And the businesses were seriously worried about how it's going to impact the access of the people to the site. So there was a ballot, and the ballot measure that went to the entire city of Phoenix basically said that if you vote yes, we're going to stop any further development of track rails. All of the money saved will be just reappropriated to other places, and then we're not going to touch this whole idea of this idea of public transportation in this particular way. And no vote, which successfully won by a grand margin, said that no, we want the light rail to extend no matter what it takes. So there was a lot of pressure for reducing the cost and as well as reducing the time that it takes. And I was asked to see if I can participate in a team that was addressing it. So the whole idea was, are we going to use some other alternative reinforcement? And my proposal was, let's replace half of the rebars in the section because of the stray current corrosion that necessitated welding of every single rebar and draining of the static electricity because of the stray current corrosion problem of the steel. So I proposed that, but then they came back and said, what does it take to take all of the rebar out? But at that point, I was stuck with the idea of let's propose, go with the highest dosage that we can feasibly work with people who have never had any experience with fiber reinforced concrete. And that was basically, and then at the same time run some fatigue tests to validate the service life of the system. So here is the problem. I mean, the single slide that can show you that in the middle of some of the busiest streets, you have to stop traffic, you have to divert with transportation cycles and implement a process where it's highly labor intensive with laying up the rebars for miles and weld every one of them and have inspection and then go through the placement. And the idea was, how are we going to eliminate all of these systems? So here's the proposal. The top figure shows the standard as plan drawing, 14.5-inch thick slab with 4 rebars, 2 in tension, 2 in compression, and on either side of each track rail, if you look at from the center line. And then you would have the hoop reinforcement, which was number 5 for carrying the load. So the idea was, let's compare the standard, which is shown on the left, which is the standard drawing and the standard application, 14.5-inch, reduce the thickness to 12 inches. So that's one of the design factors. And then use the specifically specified steel fiber reinforced concrete. So we went with steel fiber reinforced concrete. 2 companies, suppliers were contacted, and they provided their own design in terms of what they felt they were comfortable with applying it. And we test, so therefore we made 6 panels or track slab samples, and we tested them. One for original concrete, and then 2 for alternative designs. And we tested 3 samples in standard load to failure, and the other one subjected to the fatigue test. Now, so this is basically the description that I provided, control markups, as well as the 2 suppliers who provided their design recommendation. This is the pictures of, again, the current control design with the rebar cage placed, strain gauge the rebars to collect the data on the strain gauges, and then the other one, which is the standard, almost nothing. You just basically set up the rail to the elevation and then pour the concrete, fiber reinforced concrete in there. Of course, so this is a picture as far as the strain gauging of the rebars, because we wanted to test and document how much stress is the steel carrying to do the structural calculations for it. Standard procedures of making sure that the mixes work and they can be cast and finished. And now the question is, how do we do, if you only have one sample, how do you decide on the fatigue life? How do you know how it works? So we went backwards. We looked at, to simulate the response under fatigue load, we looked at the service life, 45 years. And then the question was, what is the damage criteria that we're going to look at? And the hypothetical situation was what if we have a water main failure underneath the track slab that washes away all of the ground support that's provided, something of the order of an 8-foot type of a length. That's because in our lab we were very comfortable with testing that. And then the idea is that for 45 years, nobody notices that the water line broke, and then there is no repair done, and you have to apply all of the load. The load would be defined in the context of the train car being fully loaded to 3 times the capacity, and then running it every 6 minutes, 24/7, for 45 years. So that ends up to be about 2 million cycles. So we have to test these sections at 2 million cycles of fatigue to the load which carries that specific service level loads that it has. So that was the basis. Of course, we did the Flexural test, ASTM C1609, to measure the material properties, compressive strength from a QC point of view, and then the setup is shown here as far as the track slab being loaded on the test machine. One of the things that we do with the 1609 test is to document the results in terms of material properties. We back calculate from the Flexural load deflection, the tensile properties and the compressive properties. And those can be fed into any finite element model or structural type analysis model to actually calculate what is the contribution of the fibers. So these are the 2 fiber systems that were provided. So, and then from the results, the flat part, which is the residual strength, that's where your steel fiber is contributing to the response. So those are the 2 numbers that an engineer would need to take to do the calculations for long-term performance. Basically, we refer to it as residual tensile strength or equivalent flexural strength of the section. So these are the basically preliminary tests that is done on these samples in accordance to the standards that are available. Now, the entire specimen is shown here as a run as a 3-point bend specimen. The load is applied on the rail, and the rail serves as transferring a portion of the load throughout to the support. So that load that we measure is not exactly the level of the stress that the track slab sees. It sees a less amount of load because of distribution. But the whole idea is that if there is no support, what is the cracking point that you would have in here? Of course, we have all fully strain gauges. On the side, you see it's painted. That's for digital image correlation measurement. Underneath the slab, we have LVDTs to measure the deflection of the slab. And all of this information is gathered. And I have some videos to show, but I need to get out of this mode. But I'll see if I can change it. So here is the. It is no. It's. I don't know if it's going to. There is no mouse code. No, there is. It's not on this one. It's on the next one. I will show. So these are the LVDTs. So significant number of LVDTs to measure the response, and what we can see is basically underneath the sample. So now what I'm going to do is let's see if it runs. So here you're looking at underneath the sample, as if you crawled under the sample and it's basically being applied. The load is being applied to it to cause for the static failure that we have. So you would see a horizontal crack, let me see, okay, forming an opening as the load is applied in the middle. So as the beam is deflecting. No graduate students were harmed in this test. We use the GoPro underneath the specimen. You can afford to lose a $200 or $300 camera, but safety is number one when it comes to the testing. At the same time, what you can also do is to look at how does the crack evolve and form. And we have developed procedures for detection of crack initiation and growth within a flexural sample. So within this specimen, we can clearly see this is quantitative type of work, which means that you can measure the crack opening at any and correlated with the load. So you basically develop this loop type of mechanism where you collect the data and allow for the for measuring what is the level of contribution of steel rebar versus the other one. So the results that we see is here, at least from comparison of 4 LVDT. So four instruments underneath the sample almost measure the same response. The load is increased, the sample is cracked, the load tries to drop, but the load gets transferred to the fiber. These are samples that have no rebar. Load gets transferred to the fiber. Fiber provides certain level of stiffness, not as much the stiffness of the steel, but then it deforms. How much does it deflect at the end? When you go to about 40,000 pounds, which is about 6 times the service load capacity, 0.3-inch deflection. That's what you would get. So, which is reasonable as far as the train ride, not people maybe not detecting that in the process. So, let me go to the next. So this is the type of a crack that we see. And then what we can do is to compare this result of the standard design, which is the reinforced concrete, which is shown in blue, standard design that was done, versus the 2 fiber systems, fiber 1 and fiber 2. And note that here the thickness has changed. The thickness is about 15% lower. And when I talk about the cost, the fact that you can reduce the thickness by putting the fibers was good enough for them to fund the project. That they figured that it's going to save them $500,000 per mile by just simply reducing it by 2 inches. And here, if your load for design, service load level is 9,000 pounds, which puts you at the 10, let's say a 10 kips load, or around 40 kilonewtons, you still have significant amount of safety factor embedded in the system. So this is an overkill when it comes to the design. And fibers provide different solutions. The 2 differences between the red and green are associated with the type of fiber and the amount of fibers that were provided by the suppliers. Of course, what we have done is we've done the simulation and calculation for these systems. Again, you can see that the simulation relatively well predicts it. We're not into curve fitting. Your model has to be completely independent of the test result, which means that still we're slightly off. But then when you actually compare the load deflection shown on the left versus load versus the rebar strain, we see that we're getting actually very quite reasonable result. The rebar is carrying the load, and that load carrying capacity occurs only after the fibers, after the matrix cracks and the load is transferred to the rebar. We can also compare the, again, magnify the full-scale test. If we magnify the full-scale test, we can see that the cracking shown on the blue curve, this mouse, the mouse here doesn't show on that, so that's creating a problem for me. The crack, oh, okay, thank you. So you can see that the reinforced concrete cracks, but with the samples with the fibers go much, much higher in terms of their cracking potential. So there is contribution of the fiber into the crack propagation, meaning that the first main crack, that is initiation of the load transfer, for the unreinforced, unfiber reinforced mix is going to be much, much lower, meaning that the steel feels the load much, much faster. Steel rebars feels it much, much faster than actually some of the fibers in the sample. So the strain gauge results and everything. And what is also important is that when you do the structural calculations, you see that even at this level, even at the level of the maximum load, the steel is beginning to reach the matter of the yielding. So that's why this sample just basically is just linear elastic. So the steel remains elastic for that static, for that test that we're doing. DIC allows us to see how the system performs. We can see that initiation of one crack later on becomes another crack, and you can see that the crack is about to evolve in here, and these deformations are displacement and strain maps. Again, 3 cracks forming, so this is good because we have good reinforcement in the reinforcement is causing the distribution of the load, and as the cracks are opening up, the magnitude of the opening is so small. This is the needle in the haystack that the IC equipment provide a lot of us in better understanding and characterizing the results. So here, I think, let me see. So here, just let's take a minute video. The fatigue test. So we're running the fatigue tests. 4 hertz, 2 million cycles, takes about 8 days to run the test. And here is this, but then it was done after you load the sample to the full cracking. So first you load it to full cracking, and then subject it to, the cyclic load. And this is underneath again with the GoPro capturing the deformation. So we're exercising this existing crack that we put in there, and then we can measure, do the data acquisition and measure the cyclic response and the opening of the sample at the end. This is the DIC, but this is the DIC done on the fatigue. So you can see how the crack is basically being exercised in the context of opening and closing 4 times a second. So this is a slow motion of the fatigue test that went. So maybe about 4 seconds within the entire 8 days being shown here. Am I done? I think so. So one of the analysis that we have to do is to look at the fatigue results. So we look at every 50,000 cycles, we collect the data for 100 cycles, and then you look at the load, unload, loading, unloading. And that response is used to calculate the stiffness. The question is, how much stiffness do I lose with significant cycles of fatigue? So as we go from each loop represents 50,000 cycles. So as we're going through these different loops at the beginning, initial 50,000 cycles and final 50K cycles. So for simplicity of this experiment or showing the results, we're only looking at the head and the tail end of the test results. And we collect data, so each one of these curves represents 100 cycles in that time domain. And from that, we calculate the stiffness of the sample. And here we plot the stiffness as a function of the entire cycles that is gone through. So technically, we see that there is some stiffness loss as the sample is exercised. And so there is some damage. But the average decrease in stiffness of the section post-cracking is about 7%. Is that something that we can live with? That's something that they decided that they want to do. And then we did also some structural analysis calculation, take the information of the rail, calculate the stiffness, treat the rail as a beam on elastic foundation. In other words, the stiffness of the rail helps carry some of the load and doesn't let the full force to go to the sample. It goes directly down. So it's a very simplified structural analysis model. And it allows us now to add the response of the rail, which remains purely elastic, to the, whether you have rebar or fiber reinforced concrete, that's the response. Add these two up, and you would get the responses that we measured in the experiment's load deflection. So these are shown basically for the fibers and for the reinforced concrete. So basically, the blue curve changes from one case to the other. And we can relatively see that how much does it go up to the yielding of the rebar. Again, this is just, another set of comparison. What is difference between the reinforced concrete and the fiber reinforced concrete? Mind you, we're only looking at a service level here, 10. So everything we're getting in the fiber domain is additional ductility that you can go much, much higher. But in the unreinforced, reinforced concrete, your deformation before yielding is somewhere about 0.15, not less than 0.1 inch. Next step was doing another trial batch, but this is for the crew and the staff to get familiarized, because once you approve the project, then you have to construct it, and for several months, the area is going to be contained. So now we went with 2 sets, and that clearly shows, you can see the fibers being cast, people feeling comfortable. The trial was just quite comfortable because people see that, you know, they brought a bunch of staff, but then the concrete was self-flowing. You could consolidate in terms of very easy. And this is actually the job project in progress. Set up and run. What happened in this process is that they realized very soon that the placement of concrete and placement of rebar no longer became the critical path in the project. The critical path in the project became the grading and the layout and the groundwork that takes. And that took a significant amount of time, cut back significant amount of time from the construction and placement. So they were going so fast that they had to finish and scatter their concrete casting schedule because the ground was not ready to accept the casting. So that was the part. This is probably the most important slide, because these are exact cost calculations that I got from City of Phoenix. And I think from a civil point of view, from concrete materials point of view, we need to realize that 50% of the cost goes into forming and setting up the concrete materials. When we go with the fibers, then the cost significantly decreases. So let's look at the cost. These calculations are done for a single mile of 14.5-inch track versus the same mile of 12-inch track. So everything is calculated per mile. What does it take for a single mile of track to put in town? Volume of concrete, 3651, 3129. This is the difference between 14 and 12. So 500 cubic yards of concrete. Now, rebar, 184,000 pounds of number 4 and 300,000 pounds of number 5 rebars were used. And they were replaced with 203,000 pounds, 203,000 pounds of steel. So the amount of steel was actually equivalent to the lower amount of half of the fibers, less than half. The cost is interesting because the cost of concrete was calculated at $90 per yard. That's a good cost, but you can, if you're buying so much, you can negotiate probably. 328,000 versus 281. So there is about about $40,000 cost per mile here. No, 328 versus 281. Yes, but the main cost saving is in the rebar, 554 versus 281. So if we calculate these costs and add actually inspection, which is lower with the fiber reinforced concrete, you don't have to have steel rebar inspected, and the materials testing also is much, much lower, 100, because you don't, again, you don't have to test the steel, and you don't have to, you have to do that. So the total saving comes into about $554,000 per mile. What is more interesting is that, so the savings, so for one project 554, the other one 281. So there is for the cost of steel fibers versus cost of rebar. That's the major change. $500,000 savings. The problem is if you bring in the labor and the schedule, things change. One track foot, a single foot of track slab with the original design would be $3,300. Whereas when you go with FRC, it's $1,000. It has to do with the scheduling and time and the labor involved. And when you do the calculations, you find out that for the original project that was bid and accepted, it was $17.5 million. When it was finished with the fibers, they actually calculated the cost to be $5 million. What that means is that there was a savings of $12 million when they switched over from one project to the other. And this is what we need to promote. Where does that saving come from? It basically, the project that should have been scheduled for 21 days was done in 11 days. That's a savings of 10. So the 10 days, basically you're talking about, one labor day is a crew of 10 people working. So you're talking about the costs involved with the labor. The entire mile of the track, which was supposed to take in 231 days, almost 6 months, was done in a matter of 3 months, 121. And that basically led into the calculations of 3309 versus 1030 and the savings that we had. I think they're excited. We want to try new systems, the technology. I think it's comfortable for people. and I go back to what I've said. Once people, contractors, and everybody else start working with fiber reinforced concrete, they don't want to go back and show me a project that you can do with fibers, which cannot be done. I mean, one that you can do, you have to do it with rebar, which cannot be done with fibers, especially when it comes to these types of track applications. I don't have any conclusions. I hope we can continue with this type of a project and approach. Thank you very much. I'll take any questions you may have.